Hello, welcome back. So, in the last module, we studied what is the information source. We mathematically define the model for an information source. We define the measure for information, and we also define the concept of entropy for a discrete memoryless source. So, the entropy of a discrete memoryless source was defined as shown on this slide. We have a source and it has source alphabet, and each of these elements in the source alphabet is a symbol or letter, and to each of this symbol we assign the probability of occurrence. And for discrete memoryless source, the entropy turns out to be this expression, which is summation of pk log to the base 2 of 1 by pk, and the units for this is bits per symbol. So, this is the average information which I get when I observe the output symbol from the source S. Now, today basically we will have a look at the properties of this entropy. So, we will study this property of the entropy, which says that entropy is always greater than or equal to 0, and it is bounded by log to the base 2 k, where k denotes the cardinality of the set alphabet, or it's the size of the alphabet, or you could say the number of symbols or letters which are there in the source alphabet. Now, we know that the expression for entropy is given here. Now, let us look at each of the term in this expression. So, if you look at this pj log 2 1 by pj, then it is not very difficult to see that for pj greater than 0 and less than 1, this quantity is always larger than 0. For pj equal to 1, this is equal to 0, and for pj equal to 0, this quantity again is equal to 0. Now, for pj equal to 0, to show this quantity is equal to 0, we can use simple L'Hopital's rule and evaluate that. So, just I will flash that the slide to show how to do it. So, you take the limit pj tending to 0 of this quantity, and you continue. It is very clear from this slide how to proceed, and you can show that when pj tends to 0, this quantity is equal to 0. So, what it means basically that all the terms out here are either 0 or greater than 0. So, the summation will be obviously greater than equal to 0. Okay. So, pj log 2 1 by pj is equal to 0 if and only if pj is equal to 0 or 1. So, this implies that entropy of the source is equal to 0 if and only if pj is equal to 1 for some j and all the rest are 0. So, Hs is equal to 0 will happen when this condition is satisfied, that means there is no uncertainty of the output of the source. Correct? Okay. Now, let us try to get the upper bound. Okay. To do that, basically we will use this relationship between the log x and x minus y. Now, I have plotted the equation y is equal to x minus 1 and y is equal to log x. So, from this graph it is very clear, and we can see that log x is always less than or equal to x minus 1 for x greater than or equal to 0, and they will be equal when x is equal to 1. The mathematical formal proof is also given here. I can form a function as shown here. You take the first derivative and its second derivative, and you can show that log x will be always equal less than or equal to x minus 1, correct. So, x minus 1 is always greater than log x, correct. This is a fundamental relationship which we will exploit in our module on information theory. Okay. So, based on this, let us derive the upper bound for this. So, proof for the upper bound, I will use the relationship log x is less than or equal to x minus 1 for x greater than or equal to 0. Now, consider two probability distributions in terms of p's and terms of q. Both these distributions are defined on the source alphabet S. Now, we can write this expression pk log to the base 2 qk pk k is equal to 0 to k minus 1 as log to the base 2 of E and summation of pk log. This log is to the natural base qk by pk. Let me call this as equation 2. So, now using 1, we get the following relationship. This is equal to less than or equal to using 1. This is equal to, I can write it And remember, these are the probability distributions qk's and pk's. So, the summations both are 1 and this is equal to 0. Therefore, I get this relationship This is a fundamental inequality which is used very often in the literature on information theory. And now we see that in this expression equality holds if qk is equal to pk for all k. So, let qk equal to 1 by capital K for all k. If we do that, then for this probability distribution over the source alphabet, we will get the entropy of the source equal to log to the base 2 equal to k. So, what it means that this relationship is always valid provided the conditions on qk and pk are satisfied. So, using this relationship and using this result, we can conclude So, I have proved this. This is nothing but the entropy of the source is less than equal to log 2 k. Okay? Fine. So, let us take an example of a binary memoryless source and calculate this entropy. So, entropy of a binary memoryless source So, in this case the source alphabet will be 2 bits 0 and 1. Let us assume the probability is P0 and P1 will be obviously equal to 1 minus P0. So, the entropy for this source would be equal to minus P0 log to the base 2 P0 minus 1 minus P0 log to the base 2 1 minus P0. So, we know that for this case for P0 equal to 0, you can show that entropy is equal to 0, and for P0 equal to 1, the entropy is again equal to 0, and based on the earlier result which we derived, the maximum value of this entropy for a binary memory source would be equal to log 2 to the base 2 is equal to 1 bit. 1 bit per symbol, correct. So, the binary memoryless source attains the maximum value equal to 1 bit. Now, in information theory literature, we come across one function which is very closely related to the expression given by the entropy of a binary memoryless source, in the sense, if I assume P0 to be a variable, then I can write this expression as minus P log to the base 2 P minus 1 minus P log to the base 2 of 1 minus P. Now, when I do this, then this is known as a entropy function. And this is used very often in information theory. Okay, fine. Now, so if you take this HP, what are the characteristics of this entropy function? It's easy to see that for P between 0 and 1, HP will be minimum when P is equal to either 0 or 1, and the maximum will be P is equal to half, and the maximum value of this entropy function would be equal to 1. Now, we can again mathematically prove this, correct. The procedure is very simple. What you could do is basically write this function, entropy function, take its first derivative, you will get this. You take its second derivative, you will get this. This second derivative is always less than 0 for P between 0 to 1. So, what it implies that if I equate this, the first derivative equal to 0, the P equal to half point gives me the maximum point, correct, and the maximum value is equal to 1, and based on this second derivative being less than 0, I can also conclude that my entropy function is concave. Okay. Now, given an information source with the source alphabet and the probabilities assigned to this symbols of this alphabet, if you look at the sequence which we get from here, I can group some of these symbols into one larger symbol, correct. So, what I mean to say is that suppose the output from this source, if I group them or form a subsequence of n symbols, then this group or subsequence can take how many values? It will be k raised to n, where k is the cardinality of the set alphabet associated with the source S. So, now I can assume that this new symbols which I get k raised to n is being emitted from another source, and that source I indicate by what is known as S raised to n and this is known as extension of the original source S, and since I have grouped in terms of n symbol, this is known as nth extension of the source. So, I will have new source represented as this. It will have k raised to n symbols, and I am interested in calculating the entropy of this source, extended source. Okay. So, let us quickly see how to do this. So, entropy of nth extension of the source. So, I have my original source with the alphabet given as follows. To each of this there is a probability assigned. Now, this extended source Sn will have k raised to n symbols. I denote these symbols by sigma I, where I will take value from 0 to k raised to n minus 1. Now, each of this sigma I, that is the new symbol in this nth extension, could be written as follows. It will be Si1. So, Si1 can take any symbol from this alphabet. Then you will have Si2. This basically can take again any symbol from this source alphabet, and so on. So, each of these new symbols will have n symbols from the original source alphabet. Okay. So, now we will assume that the source is a discrete memoryless source. So, if we do this, then the probability of sigma I is equal to probability of I1 multiplied by probability I2 up to probability In. So, let us calculate the entropy of this source. That would be equal to minus summation p sigma I log to the base 2 of probability sigma I, and this should be sum over all the symbols from the extended source. So, this can be rewritten as which can be rewritten again okay, fine. Now, let us look at one of the term in this expression. Let us take the first term without loss of generality. So, if I take the first term, this I can write it as and this I can rewrite it as okay, fine. Now you see basically this all these summations are 1. So, and this term out here, sorry, this is minus sign out here. So, this term is your entropy of the source. So, going back to this expression, each of this basically is equal to Hs, and we have n terms like this. So, what I get is that entropy of my nth extension of my original source turns out to be n times the entropy of my original source. So, in this class we learnt about the properties of the entropy. We showed that entropy is always greater than or equal to 0, its value, and it is bounded by the log to the base 2 k, where k denotes the cardinality of the set alphabet. We also examined as an example the entropy of the binary memoryless source, and we derived the entropy of an nth extension of a source and showed that it is equal to n times the entropy of the original source.